Hello folks, we come to the exercise 1.3. This is a part 1 video, and we will be taking up these values of GOF. They have given us a function f which is from the domain 1, 3, 4 to the 2, 1, 2, 5. We have a function g from 1, 2, 5 to 1, 3. Let us see how we can define this composition GOF. What we are going to do is we'll try to understand this pictorially with the help of this arrow diagram, and then we will try to see how the GOF function is getting defined. This function f is defined from 1, 3, 4 to 1, 2, 5. This is the function f, and this is the function g, which is defined from 1, 2, 5 to 1, 3. The function defines like this: 1 goes to 2, 1 goes to 2, 3 is related to 5, and 4 is related to 1. This is our function f. G function is defined such that 1 is related to 3, 2 is related to 3, and 5 is related to 1. This is our function f and g in pictorial form. They ask us to find out the composition GOF. Composition is nothing new to us. We have seen it in the earlier classes. So we will see now how to get the composition. They have asked us to form a function GOF just like this. So GOF, because it is defined, starts from f. Actually the function GOF will be defined from 1, 3, 4 to 1, 3. Right, f and g, how it is coming like this. GOF will start from here and it will end here, that way. So let's see the definition. GOF at 1, that means it is g of f of 1. That's the definition of GOF. F of 1 we know what it is. F of 1 we know it is 2. We know that f of 1 is 2. F of 1 is 2, right? Then we have to see what is g of 2. G of 2 is 3. G of 2 is 3. So we have finally GOF of 1 as 3. Now let's take GOF of 3. GOF of 3 means g of f of 3. F of 3 is 5 and g of 5 is 1. GOF at 4 is g of f of 4. So f of 4 is 1 and g of 1 is 3. Finally, they have asked us to find out what is the function GOF. So GOF basically is 1, 3, 3, 1 and 4, 3. So this is how our function is, and this is what they are asking us about the function GOF. Now once that is done, we are going to the question number 2, and in the question number 2 they ask us to show, they have already given the function f, g and h, which is defined as a composition in this particular way. They ask us to show f plus GOH is FOH plus GOH, and f dot g, f into g, OH is FOH dot GOH. So okay, quite routine. We do our proof and we'll see how we get the answer. So let's take the first subpart. In the first subpart we have f plus GOH. So let's consider f plus g, composition of h, OH. Now a function has to be defined at a point, otherwise it's meaningless, right? So for our convenience, we'll take it at a point x. Now O for us, we always know it can be written as f plus g of hx. See, we remember, because when it was GOF of x, we wrote it as g, and this O is converted as a bracket f of x. So here this is converted as a bracket in h of x, right? So we have it like this. Now what has happened? You have the function f plus g at hx. Okay, so it's a point. Hx is a point. So therefore, looking at the definition of the function, it's very clear that it is this f plus d which is defined at this point. By looking at the algebra of functions, we can say that this is always f of hx plus g of hx. That's how the function's algebra is. Two functions, if they add it, this is how the function takes its values. So we have f at hx and g at hx, but that is as good as saying FOH at x, and this is as good as saying GOH at x, right? That's how we define the composition. So you've got FOH at x and GOH at x. So that is as good as saying FOH plus GOH because of the algebra of functions. That's how the algebra of function is defined. So you have it like this. Now when we see both the sides, we had applied x and that's how you've got the function. That's how you get f plus g OH as a function becoming equal to FOH plus GOH. Hence proved. Right? So this is how we are, therefore, hence proved. Right? So quickly so on, we'll move to the next subpart where they ask us to take the product and try to prove that. So same way we will also consider that part. Consider f into g OH. Let's apply it at x, because unless a function is applied at a point, we are not able to trace out how the function works. So let's apply it at x. Now we know that this composition always means replacement by a bracket. So f into g, the product of function, is defined at the point hx. That is also an element where it has been defined. And according to the product of functions, if it is defined at a point, it is as good as saying f of h of x into g of h of x. That's how a function is. If a function is defined at a point, if the product of a function is defined at a point, then it gets individually distributed like that. So this is how it is. But this, by definition of composition, can be called as FOH at x, and this is called as GOH at x. Because they are both getting applied at x, there's no harm if we call it as FOH dot into GOH at x, because it's clear that in a product it distributes to individual things. So we have got it like this. Thus, starting with f plus g OH, we've got it as, f dot GOH, it is f OH dot GOH. That's it, henceforth. That's about it, and that's our problem number 2, subpart 1 and 2. Now we'll quickly move to problem number 3, subpart 1, where they say that they give us a function f of x, which is modulus of x, and they give us a function g of x, which is modulus of ix minus 2. They ask us to find out both FOG of x and GOF of x. It's a good example. Why? Because we get to know the composition much better. We'll understand, how you can do the composition. When we do such examples, the idea of composition, these kind of examples are very good for you to understand what the composition is. So that will help you to get the composition clearly. So let's right away find what is FOG at x, which means by definition it is f at g at x. G at x, but by definition is modulus of 5x minus 2. What is the function definition? F says that whatever is here, it will become its modulus. So whatever is here, it will become its modulus. That's all. That's FOG of x. Now we will also find out GOF of x. G of f of x means G of f of x. So that is modulus of x, we know it. G of x means it is first modulus, then phi, then whatever is there in the bracket after g, right, minus 2. Haven't we applied it properly? So that is the function FOG of x and GOF of x. That's what they have asked us to show, and this is how it comes. So this is our problem number 3, subpart number 1, and that we are done with more problems. Exercise is full of problems that we are coming with in the fresh video. Thank you.